Welcome to Exploring Computing.
The topic for this lecture is the various subfields of AI. And the reason I want to talk about this is because we often hear of the terms machine learning and neural networks and deep learning and reinforcement learning, so on and so forth, without really knowing what they actually mean. And oftentimes they're used more as a buzzword than anything else. Now, this won't be a comprehensive list in any way, but the goal is to have a general idea of where these commonly used AI terms fit in with respect to each other and what they really mean. If the entire screen is the whole world of AI, then the largest subfield, at least for now, is machine learning. Machine learning can be understood as the study of algorithms and statistical models that computer systems use to effectively perform a specific task without using explicit instructions, relying on patterns and inference instead. Now, that was a whole bunch of words, but it'll be more clear as we go into the subfields of machine learning. Of these, there's supervised learning. Supervised learning is when we have models whose data that it's trained on consists of its inputs as well as its expected outputs. It's called supervised because we know what the right answer is, and so we're telling it, if given X, you should give us Y. Now note that the inputs X can consist of more than just one input. So oftentimes we'll actually write X as X1, X2, so on and so forth, till Xn. So in this case, there would be n different inputs, and it would give us a specific output Y. So an example of this would be predicting housing prices, where the inputs might be square footage, the number of bedrooms, the number of bathrooms, and the output would be the price. And so the data that this model is trained on would be this table filled out. So in this case, X1 is the square footage, X2 is the number of beds, and X3 is the number of baths, and Y would be the price. And so once this model is trained with all of the data that we have, we will be able to predict based off of what we put in as the square footage, the number of beds, the number of baths, and the model will predict a price that the property should be. Now, within this framework of problems, there's many different algorithms that can be applied, but perhaps the most commonly known one would be linear or logistic regression. You might have seen this in some math or statistics classes, but basically what you want to think is line of best fit. So you have a bunch of points and you're trying to fit the best fit line to it. So in this example above, we have a bunch of points, and the line that we're trying to fit is these values over here. And so eventually, once you get the line, you can plug in your own point and figure out where it falls on the line. I'll go much more into detail on this in the next video. One way that we can represent this model is to draw a picture. So we have a bunch of inputs, X1, X2, X3, and we want to pass them all into a function. So we'll go in there. And the function should represent a line of best fit composed with a nonlinear function. And finally, the function will output a Y. Alternatively, we can use another approach, which would be neural networks. The idea behind a neural net is that instead of only having one of these functions, we will chain a bunch of them together. The reason we call them a neural net is because we use ideas from cognitive science about the neurons that we have. So if you've taken a biology class about the human brain, you'll know that it is made up of a bunch of neurons that are connected to each other. A neuron takes in the outputs of a few other neurons and gives an output of its own. And if you look at this picture over here, this kind of captures that idea, right? So here it takes in multiple inputs and it gives an output. So if we make these inputs the outputs of other neurons or other functions, then that will be a good approximation of the brain. So a neural net will take in a few inputs and pass them into multiple functions now. Pardon the messiness, but basically every single one of those boxes represents a function, and each function takes in all of the possible inputs. And we can further chain together even more functions, which take in the outputs of the previous functions. Each one of these levels that we have are called a layer, and each layer can have any number of neurons inside. So it's a very flexible structure. So of course, to make things even more complicated, there's a bunch of different types of neural networks, and perhaps the most commonly referred to one is a deep neural network. And to understand a deep neural network, it's basically a neural network that has a bunch of layers that are all connected to each other. And now we've gone in pretty deep, pardon the pun, so let's backtrack a little bit. And so within the realm of machine learning, we had supervised learning. And so in contrast to that, we also have unsupervised learning. Now, before I zoom in and fill out the box, recall that the reason why we called supervised learning supervised was because the data that it received and was trained on consisted of the X's, which were the inputs, but also the Y's, which is the expected outputs. Now, for unsupervised learning, we no longer have the Y's. This set of algorithms can be really useful for when we don't even know what the answer is supposed to be, and we're just trying to find trends in the data that we have. So there's many different algorithms that fall into this category, but an example problem that can be solved is, let's say we had a bunch of points that only have two features, x1 and x2. And since each point will have a different x1 and x2, we can graph this on this chart. And while we can visually see as humans that there's two different groups, unsupervised learning algorithms allow the computer to see this as well. And this can be very useful for humans as well, because we aren't always able to see the different groups of data. Note that in this case, there's only two different inputs, x1 and x2. Now imagine if there were 17 different possible inputs, or even 1,000 different inputs. How do you group all of these points together? A unsupervised learning algorithm would be able to tell us that very effectively. From an application standpoint, something like this can be used to figure out consumer trends and target ads towards people more specifically. So we've seen from the privacy and security lectures that there was a woman who's targeted by Target for pregnancy-related ads. And so what most likely happened was they noticed that she had specific shopping trends, and so perhaps the features like X1 and X2 were the different kinds of things that she bought, and they put her in a group that consisted of mostly pregnant women. And so that's how they knew that she was potentially pregnant and started giving her ads for pregnancy. Now, in addition to supervised and unsupervised learning, there's also reinforcement learning. And this is a little bit different than the previous two because instead of having a huge amount of data, we don't have any data at all. And instead of trying to learn the model, we already have a pre-existing model. And what this model has are the different actions that an agent can take in each step, as well as a reward associated for taking an action at a specific time. There are some other things as well, but for now, just think of it as there are actions and rewards. And the reward aspect of this model is where the reinforcement comes in. The goal of the algorithm is to maximize the overall reward that it can obtain over time. So from a practical standpoint, one application would be to figure out how a Roomba should move across the room while it vacuums the floor. So let's say we had a Roomba that was in a room, and the room can be represented as a grid. So suppose the Roomba was here, and there was trash over here, and then over here, and over here. So in this case, this model will have a positive reward associated with the squares that have trash in them, and a neutral reward in the squares that don't have trash in them. We can also designate grid spaces with negative rewards to represent spaces that we want to avoid. So the goal of a reinforcement learning algorithm would be to figure out which way the Roomba should go in order to maximize its rewards. And so in this case, the actions would be either up, down, right, or left. Now, perhaps if the Roomba didn't really care when it received its rewards, then the best sequence of steps would just to be go around the room in a grid-like fashion and collect all of the pieces of trash, and that would be perfectly valid. But If the model was set so that the rewards are worth more if they're obtained earlier on, then perhaps the best course of action would be for the Roomba to first move up and then move right, and then go down and then move to the right. We can also specify the reinforcement learning model to take into consideration how much power the Roomba has left. And so let's say the Roomba only had 5 steps left. So in this case, instead of moving up to collect that one reward, it would make more sense for the Roomba to move down 1, 2, 3 steps and then to move right 2 steps. And that way it'll get a reward of 2 instead of only a reward of 1 and be unable to reach the other 2. So in general, a reinforcement learning algorithm is able to maximize the amount of reward over time by taking the optimal actions. So all of the examples and subfields that we've talked about so far have fallen into the category of machine learning. So now let's look at some non-machine learning subfields. Now, this is where it gets a little bit complicated because there's a lot of AI techniques that use a combination of both machine learning and non-machine learning techniques. So everything that I'm about to list most likely has a significant amount of overlap with machine learning. One example would be artificial speech. This includes technology like text-to-speech and speech-to-text. The goal of artificial speech is to translate from audio to text or vice versa. In both cases, speech focuses on the words being spoken, but not the meaning. On the other hand, we also have natural language processing. This is often referred to as just NLP, and it focuses on the meaning behind the words being spoken. So examples of NLP include sentiment analysis, which is figuring out the sentiment behind a sentence, as well as machine translation, so translating between words or sentences or even paragraphs. Notice that the distinction between the two is sometimes blurred, and that's because there are a lot of systems that actually use both. So for example, when you tell Alexa to turn on your lights, it uses both speech recognition by transforming your speech into text and also some sentiment analysis to figure out what you're trying to actually get Alexa to do. The reason why these two aren't considered strictly machine learning is because we oftentimes will explicitly program some additional information to these systems, which means that we're violating the without explicit instructions definition of machine learning. We might give an NLP system a built-in dictionary because we already readily have that information and there's no need to repeat that amount of work. Or we might explicitly program in the grammatical structure of our language to better aid the speech-to-text translation. However, in addition to these explicit instructions, these systems often use additional machine learning techniques such as deep neural networks to accomplish its tasks. And just as an aside, we also refer to deep neural networks as deep learning. So if you've ever heard of the term deep learning, that's what it's referring to. Another subfield would be planning, scheduling, and optimization. And there's a huge overlap with reinforcement learning because the Roomba problem also falls into planning, scheduling, and optimization because it's trying to figure out what the best sequence of tasks should be. Another example of a task that would fall into this category of problems would be how to optimally schedule classrooms given time and room constraints. We also have computer vision, which takes in videos and photos and tries to determine the subject of these media. And there's also a huge overlap between this field and neural networks, but we also add in the hard-coded things like facial features and so on and so forth. And we also have the subfield of expert systems. These are systems with hard-coded rules for logical deductions. So it contains a knowledge base, which is a set of facts known to be true, and also an inference engine. And it uses the inference engine to deduce new facts from the known facts. So for example, if we already know that if it rains, then people use umbrellas, and we also know that it is raining, then the inference engine can be used to deduce that people are using umbrellas. And finally, we also have the field of robotics. And perhaps this one overlaps many of the other ones because it's so broad. So for example, we have things like Roombas, which would make use of both planning, scheduling, and optimization, as well as reinforcement learning, as well as computer vision. And we also have but then we also have robots whose main task is to try to emulate the way that humans walk. And this is a machine learning problem where we're trying to figure out how to maintain balance when walking. And finally, we also have things like automation robots. And so this could be an AI problem about how to automate tasks the most optimally, and that could perhaps be in this optimization category as well. At the end of the day, the field of AI is extremely interdisciplinary, and so I think that the subfields of AI follow that trend as well. And that's why there's so much overlap between the various subfields of AI that we've seen today. Note that none of these boxes are really drawn to scale. There's really no way to measure how big each of these subfields are. Furthermore, all of these edges should be made very blurry because there's so much overlap between the various subfields. However, I hope that in the process of drawing out these boxes and going through the thought process between categorizing each subfield, I have given you a better idea of how these subfields might relate to each other and what they are.